Hello and welcome to today's webinar. My name is David Cash and I'm a member of the marketing team here at Mountz. I just want to say thank you very much for joining us today on our topic as we look at how to select an electric screwdriver. Now, if you have any questions during the presentation, feel free to type those in to the chat and we'll look at those at the end of the presentation. So let's go ahead and jump right into how to select an electric screwdriver. Now, anytime that we do talk about our fastening products or our webinars, if you've been with us or joined any of those previously, we talk a lot about the fastening risks at the beginning of the presentation. And if a fastener is over-torqued, that can really present a problem. It may push that fastener past its yield point, and any type of normal use will cause that fastener to break and fail. Conversely, if the fastener is under torqued, any type of vibration could cause that fastener to allow parts to not be secure, again causing the fastener to fail or break because it's not designed to hold the products when they or components when they may move or shift. There's also the human element that is involved with any type of error of fasteners not being torqued or skipped or missed or even cross-threaded, things like that. So when we look at how we can best look at what problems we have, how we can solve those, look at our processes, this can really help in determining which tool is going to be the best use of for our particular scenario, or in this case, your particular scenario. So something that comes up quite a bit is going to be a static torque versus a dynamic torque. And in often cases, you can relate the static torque to more of a hand tool operation where the torquing process may be a little bit slower because of the torquing action happens at one particular moment. There's not as much build up to that particular process as it would be with a dynamic torque tool, such as a power tool, electric torque screwdriver, or pneumatic or pulse tool, where we have some inertia that is going to be generated after that particular fastener has been torqued. And so you may hear that term static versus dynamic. And that's typically what it is dealing with. And so with an electric screwdriver, we are talking more about a dynamic torque process where inertia can play a role in the final torque that is being used. And so when we look at why we would want to use an electric screwdriver, so maybe we want to move from a static torque type of tool to more of an automatic or electric tool due to the product material that we're using or the amount of volume that may be used with the that application. So we want to try to be more efficient with that. Maybe moving from a pneumatic style of tool where there may be some particulates from the exhaust that may be contaminating the area, or you're switching from a pneumatic style of tool to an electric tool in that case. And so some of the factors that can play a part in that, first is going to be the type of material that is being used. Is the fastener going into plastic? Is it a self-tapping type application? Are you using metals that once they come in contact may have a natural reaction to fuse together? What type of coatings might be on the products, the fasteners, the washers, nuts and bolts, and things like that. So the material can play a factor in the selection. We're also looking again at the volume that may be needed. Torquing down a PCB board on an assembly where there may be 40 fasteners may take quite some time to do that with a hand tool. With an electric tool, that obviously is going to allow the operator to be much more efficient and be able to get that done a lot quicker. We could also look at the RPM that's going to be generated. We touched a little bit on this on the dynamic portion, where RPM can influence the final torque. So if you're dealing with a really low torque value, the faster in RPM, that may generate more inertia at the final torque than it would be if we're able to keep a lower RPM for those lower torque values. So RPM is going to play a factor in that. And another component is going to be ESD. If you need to protect components from electrostatic discharge, that may be a consideration for the selection of the tool that you may be purchasing. Is that tool ESD safe, or is it ESD compliant? And then finally, we're looking at the actual fastening joint and the characteristics that make up what happens when that fastening is done at that particular. When we are talking about different joint characteristics, there are classifications of joints. So a hard joint would be considered 30 degrees of movement or less when the fasteners mate, or the surface of the fastener meets the top of the surface. 720 degrees of rotation, once that happens, would be considered a soft joint. And so these are some things that can place an emphasis on what happens during the torquing process. And so some of the other variables that go along with that could be the use of a gasket, for example, we talked about for a soft type of joint. There could be some lubricant that may be added to that fastener that's going to cause a variation in the amount of clamp force that's generated during the rundown period, because the coefficient of friction has now been reduced. It could be the actual material that is being used. Again, the RPM that may be used. At a higher RPM, are we generating too much heat that may be affecting the materials and how it reacts during the torquing process? Could there be variable torque because of the actual prevailing torque that may be within that fastener? Is there a security patch or a nylon lock that we're trying to cut through? All of those things can and do play a part in the variations that can happen during the torquing process. And so when we look at the different types of screwdrivers, and there are a lot of different ones that have a lot of different features for a specific type of application. And so, for example, this first driver that we're looking at is a direct plug-in driver, meaning that the power cord that comes off of the tool plugs directly into an outlet. And so in this case, this would be good use during a very low volume type of application where the duty cycle is quite low. So meaning that you're running a fastener down, the tool has time to rest. You run another fastener down, the tool has time again to rest, because the transformer is now built inside of the tool. And if that transformer gets too hot, obviously we have the possibility of that tool failing. Now, if we look at, again, the specific requirements for this tool would work great under those types of low volume, low type of duty cycle for the tool to operate in. So a typical duty cycle for this would be 1 second on and maybe 3 seconds off. So there is time to allow the tool not to overheat during the fastening process. And that would be the direct plug-in style of tool. Now, the advantage to this tool is that it is less expensive than a tool that has a transformer or a dedicated power supply to it. But again, for the right application, a direct plug-in tool will work just fine. Next is going to be the transformer style tool that we have just talked about. This is going to be used in a real high application or a high volume type of application where the driver is going to be fastening one after another, which has a much lower duty cycle than the direct plug-in style of tool. And with this, the transformer tool may have some additional features built in within the transformer that would allow it to change the RPM speed of the tool from maybe a low to a high, or it may allow for additional accessories or peripheral devices to be plugged into the transformer to help with error proofing or screw counting and things like that. So the transformer can add a little bit more of a benefit to the fastening process depending on the application that you would need. But typically a transformer style tool is going to be used in a higher duty cycle type of application. Next would be a screwdriver that is going to allow you to adjust the RPM for the application. So if you have a tool that maybe you want to use in different locations at different times and you want to be able to adjust the RPM, you have that capability to adjust the RPM in this style of tool. So you have increments starting, maybe it's 50 RPM increments or 100 RPM increments, depending on the style of tool that you can adjust to. So if moving or adjusting the RPM is beneficial to you, then this would be the screwdriver for that. Next is going to be a soft start feature. Some tools are equipped with this to help against cross-threading. So it starts the fastener at a slower RPM and then we'll move up to the operating RPM. And in some cases, this style of tool also allows you how much time you would like that soft start to be. Does it need to be very short or does it need to be longer because of the thread characteristics of the fastener? So a soft start feature is something that is also possible. And again, this is going to be for those really fine thread type of fasteners where you want to try to avoid any cross-threading type of issues. Next is going to be the soft stop feature. So if you've got a real delicate type of application that you're working with, you don't want to add any additional shock to the components when the tool shuts off. We have a soft stop type of feature that is available as well. And then additionally, we have push to start electric screwdrivers. These are typically a style of tool that you may have operators that are used to using air tools that were push to start, but sometimes the push to start tool doesn't give you as much control over the fastening process because once the operator pushes down on it, are they meaning to push down on it at that time? Does the fastener or is the tool on the fastener? And so some of these types of issues can happen with a push to start type of tool. And so that is one thing to keep in mind when you're looking at how the tools actually will begin the process. Majority of electric screwdrivers are lever to start, but there are push to start models available as well. So this is going to bring us to our poll question. So our poll question for today is what type of an electric screwdriver are you currently using? And so we have lever to start, push to start, robotic screwdrivers, or our cordless, or not our cordless, but a cordless screwdriver. So I'll give you a few seconds to answer that. All right, thanks very much for your participation. It looks like the majority is lever to start, but it is a little bit equal across the remaining answers. So again, thank you very much for participating in our poll. So as we continue looking at the different types of tools, electric drivers, there are two categories that are tools that contain a brush motor and tools that contain a brushless motor. And so kind of what the difference between a brush and a brushless motor is, well, it's kind of simple. There are no brushes in a brushless motor. So if we take a look at a standard DC motor, it is an electrified circuit. And so we have magnets that have a positive and a negative polarity to them. And in this case, in our example, there's an armature that through the electrified circuit becomes electromagnetic, and it is either pushing or pulling towards the opposite pole for its circuitry. And in this case, for the rotation to continue to happen, we have multiple armatures that are connected to the commutator, and the brushes then are attached or pushed against the commutator, helping to either switch the polarity on the armature to create the spinning motion of the motor. And that's typically how that works. Now, those brushes are in contact all the time, and eventually they wear. And now they're designed that way. There are springs that are constantly pushing the brushes into place, so we can have that electromagnetic circuit continue. And so if we look at that on a standard motor housing or componentry, we have the area where the brushes are. Those brushes, again, are providing the circuitry to allow the armature to spin. In this case, the shaft is rotating. So the entire motor assembly is rotating, and the brushes are still. And over time, those brushes begin to wear away. So they are made of carbon. And so in the case of the brushless motor, it's kind of the opposite of what we looked at before. And so we have now the electrified circuitry happens on the inside the componentry, and those are controlled electronically to be able to change their polarity, and so they can push or pull on the magnet, again now providing the rotation that is needed, and that happens now with the opposite. So the entire housing is rotating, and then that housing is connected to the shaft of whatever is rotating, and so in this case there is no contact between the componentry, again now making it a brushless system. And so when we look at the particulate that may be produced by the carbon brushes, if you take a look at this example here, on the left side is a housing on the inside that has brushes. So the carbon eventually will wear out and be dispersed throughout the tool. And again, on a brushless motor, that does not happen because we're not producing any particulate there. And so that is kind of the brushless versus the brush. And so with a lot of the different types of tools within the electric categories, there can be a brush version or a brushless version. Now, the benefit of using a brush tool is that it is less expensive typically than a brushless tool. And that again deals with the motor componentry and the sophistication of the electronic circuits that are being used to generate the rotation in the brushless type of motor. So if we look at additional types of screwdrivers, in this case we have a clean room driver, and you can see that this is a brush motor in a clean room environment because of the additional vacuum that is a port on the side of the tool there that is constantly pulling any particulate out of the tool that's being or as it's being used, as those carbon particulates are being generated by the contact of the brushes. That is being sucked away by this vacuum system. And in conjunction with that, there is a vacuum pickup on the end of this tool. So this allows for the use of a screw presenter, and then the tool can just come and pick up the fastener by use of vacuum to put the tool tip and the fastener together without the operator having to pick up the tool. This is also available without the use of the additional port on the tool. So if you're looking at a standard vacuum pickup for a brushless style tool, then this is what you would see. Again, the mouthpiece goes over the fastener, and then it gets brought up to the tip of the tool, and then the operation can go ahead and take place. So these, additional types of drivers are going to be robotic style tools that are controlled either by an automatic assembly process or possibly a robot or a cobot, those types of drivers. There's also cordless versions of the torque tools. In this case, this is our EPT, which is our cordless transducerized DC tool. And then there are also DC corded tools. And if you need information on these styles of tools, we have done complete webinars on our DC control systems. Feel free to look at those. But these tools give you the most control and flexibility in dealing with your applications. And so if you have any questions on those, feel free to look at our past webinars on the DC control tools. And so with that, let's go ahead and look at some of the accessories that are available. So you could have a pistol grip attachment, a right angle tool attachment, tool balancers to suspend the tools, screw presenters, torque arms. There are also torque covers to prevent the tools from the torque accidentally being changed. And we'll look at that in our demo portion of today's presentation. And there also can be screw counters to help with error proofing in the assembly use of the electronic screwdrivers. So with that, let's go ahead and jump into our demo. And so what we have here are a number of different styles of electronic torque wrenches. And the one thing that all of these tools have in common is that they are controlled by a spring clutch. So there is a spring in the cone of the tool here, and that spring will determine the actual torque value. And so if I remove this cone altogether and expose the spring, you can see in this case, this is a black spring, and different spring colors may have different characteristics about the range that it functions within the tool. So in this case, for the range of this tool, we're using the black spring. And now on the tool itself, there are some indication marks here that will tell us as we move the cone, a reference to whatever torque is being produced at this reference point. So these numbers on here do not correlate to actual torque, but they're just a reference for when the tool is set on a torque analyzer like this. And so we'll show you that here in just a second. But here are the different, like I said, a number of different styles depending on the torque range. If they are a brush tool or a brushless tool, the easiest way to tell is that in this case, this tool right here is brushless because there is no spot for a brush to be inserted. So we can surmise that this is a brushless tool. This particular tool does have the ability to change the RPM, and this can be set with the use of the transformer, and this is completely locked once it starts. It also has a soft stop feature as well. So this would be an example of a brushless tool with adjustable RPM and a soft stop feature. So with that, we can, again, depending on the size of the range of torque that we're dealing with, you may use a larger type of tool that can go up to a higher torque value, and that would be the case for this series of tool. This one can go up to close to 39 inch-pounds or so, as opposed to a smaller unit that may only go up to a couple of inch-pounds with that. Now, again, these particular tools all use a transformer to control the actual power output. And as I mentioned earlier, this one does have the ability to use some peripheral devices through a port that can be utilized, and other transformers will have maybe a high or a low RPM that we can use for the actual adjustment of the RPM if that particular tool and transformer allow for that. So let's go ahead and show you how you can demonstrate or set up a specific tool to a specific torque value, or to determine if that tool is repeatable. So I have our torque analyzer here, and we'll go ahead and use this tool. Now this one is one of the direct plug-in style of tools that we looked at. So this is simply just coming out of the tool and directly into the outlet. And we will use a rundown adapter for this. So this particular rundown adapter allows us to be able to simulate what happens during the actual rundown. So this allows for the tool to get up to its operating speed and then shut off as it would during the actual torque delivery process. So let's say, for example, we want to take our direct plug-in tool and we want to set this for at around 8 inch-pounds or so. We can go ahead and do that. Let's go ahead and use our rundown adapter. We'll pop that into the analyzer and then use our bit in the tool. And again, as we make adjustments to the cone of the tool, this is going to allow us to be able to change and set the torque value. So let's go ahead and run it down and see where we're at right now. So around 10 or so, 11 inch-pounds. So let's go ahead and turn this tool down. Okay, so we did not turn it down that much, so let's go ahead and do that here. I'll leave the tool on the analyzer. Okay, at this point, if we want to test the torque value of a specific tool that we're using, or we want to see if that tool is repeatable, we can do that with the use of a torque analyzer. Also, we'll need a joint simulator or a rundown adapter. This helps to simulate the actual fastening process, allowing the tool to get to its RPM, its operating RPM, and then it will go ahead and shut off, giving us our torque output. Now, again, the cone indication of where the tool is at a specific reference point is going to allow us to see what that may correlate to the torque analyzer. But in this case, let's go ahead and test our tool. We're at a reference point right around 3 or so. We can then go ahead and set our tolerance or our target torque, what we're looking for on our analyzer. And so let's say we're shooting for a target of around 8 inch-pounds or so. So let's go in and set our analyzer to read at 8 inch-pounds. And go ahead back to our operation. And now we have our target at 8 inch-pounds. So everything that is basically going to point straight up in our readings is going to be right at 8 inch-pounds. Anything above or below is going to be out of tolerance for our specific tool that we're using. So let's go ahead and test that and see where we're at with our torque value. And if we just put the tool into the rundown adapter and go ahead and run that down. All right, we're at about 11.5 inch-pounds or so. So that means we need to basically turn down the tool or move the collar away from the body of the tool. So by doing that, we can turn it counterclockwise. And let's move that down a little bit more and then do another test and see where we're at. All right, so we're right about 9 inch-pounds or so. So let's go ahead and turn that down a little bit more. And that is at 8.1. And so if we are happy with that, we can leave it there, but let's turn it down just a little bit more. Maybe just 2 clicks. And if we're happy with that, we're right at 7.9. Then we can go ahead and lock the collar in this position. Now, this tool does have a little set screw that we can use to lock the collar down. We also have torque covers that can come over this and help prevent the operator from accidentally changing the torque setting, or in some cases, operators may have the tendency to change it on purpose. We have seen other companies that will actually put heat shrink over the end of the cone here to help prevent that from moving. But that's how we can use the torque analyzer and set up the tool and check if it's repeatable. So with that, let's move to any questions. Chris, do we have any questions?
All right. First question, Dave. We have an application where we are fastening screws into plastic and experiencing issues with plastic cracking when using a power tool. How can we stop this from occurring?
So there could be a couple of factors that could be playing a part here. First, you might want to take a look at the fastener itself. If the threads aren't coarse enough, this could allow the fastener not to grab enough material, and that may be a component of it. The other factor could be the RPM. If the RPM is too fast, then the fastener may be blowing through the material, not giving it enough bite, or so to speak. And then if the additional inertia that's caused when the tool shuts off, that may be contributing to it well. And of course, the actual torque that's being used for that may be too much for the fastener to be able to hold in place. And so all of those factors could contribute to the fact that parts are breaking. And so if you look at those different factors and do some testing, that may certainly help move you in the right direction.
All right. Thanks, Dave. Second question we have is, we experience cross-threading events when our operators start fastening screws with the power tool. How can we prevent this?
So we touched on this briefly when we were talking about a number of different styles of torque screwdrivers. And if you want to help prevent any type of cross threading, you can use a soft start feature where the tool will start at a much slower RPM, allowing the tool to fully or allowing the fastener to fully engage and then ramp up to the running RPM. Another assembly strategy is to have the operators start the fasteners by hand, but that again is going to defeat the purpose, or not defeat the purpose, but it may end up taking a little bit more time, and you could be more efficient with a soft start feature.
All right, question 3. How can we verify the torque setting of an electric screwdriver?
Well, as we did in the demonstration portion of the presentation, we can simply use a torque analyzer with a rundown adapter to set, verify, and make sure that the tool is being or is producing the amount of torque that's needed for the application, and to make sure that the tool is repeatable.
All right, Dan, thanks. That looks like that's all the questions we have.
Okay, and with that, we'll go ahead and wrap up today's session. Thanks so much, and we look forward to seeing you in the next one. Have a good day.